induced seismicity. And so what I'm talking about today is trying to develop sort of reservoir models and seismic hazard assessments using sort of AI methods of clustering and data fusion. So geothermal energy is basically the heat that's stored beneath the surface. And it can be used for heating, cooling, electricity. And it's also a sustainable source of lithium, which one needs for batteries, which is important in the electrification of cars and whatnot. But in order to have a good geothermal system that can produce all this energy, you have to have three key elements: heat, fluid, and permeability, or basically the ability for fluids to move through the subsurface. And this is important because you need to have a economical sort of geothermal system that can produce a lot of energy and make money and be cheap for people. And it's also important in terms of global warming because with geothermal, very little greenhouse gases are emitted, unlike with traditional petroleum carbon-based oil and gas. So in order to make a system economical, sometimes these are not ideal situations, and you have to create a made reservoir with better permeability or better ability for fluids to flow through the subsurface. And when this is the case, people pump down fluids to cause pre-existing natural fractures to reopen, generate additional fractures, which increases permeability, and the effective porosity, also the storage capacity of your system, which allows you to actually circulate fluids and generate energy. So the problem with this is if you pump down enough fluid, you can generate seismic events that are large enough to cause damage, such as in Basel, Switzerland, or Seoul, where the geothermal systems were actually shut down. So all of the geothermal projects that are out there, one of the first steps they have to do is to identify seismicity risk, and appropriately have plans in place to deal with it if it becomes a problem. So the way people do this is they have to make a big study of the subsurface, understanding the geology and the structure, where the formations are, the rock properties of the subsurface, what pre-existing fractures are there that you could have an earthquake on if you start pumping fluids there. And then they do a variety of different empirical and physics-based models trying to integrate all this data. But it's a bit of a challenging, and it can be very computationally expensive. So we wanted to try and address this and see if we could use our AI methods to do this. And so the approach that we're doing is we're developing sort of this pre-stimulation Earth model that's sort of 3D properties throughout the whole subsurface. And then we actually apply this hybrid clustering algorithm to identify different clusters and different sets of properties in the 3D subsurface that could be associated with increased seismicity and increased seismic hazard and risk. And then the expert can take a look at those clusters and assign seismic hazard classes. And the data we're using is actually this forage system in Utah, which is in the western United States. And it was set up by the Department of Energy to provide sort of a publicly available laboratory to develop geothermal systems to make it marketable. And it's been going for several years, and they've drilled at least 3 different wells and taking constant measurements. And all the data is publicly available, so anybody can take a look at it and look at the reports. And it's really a good comprehensive data set for us because it has temperature, stress, porosity, permeability, and sometimes in other sites, the data is much more sparse. So first step in our project is to develop the Earth model. We use temperature and pressure data, stress, which controls the direction that your events will fracture in, porosity and permeability, which basically is the capacity to hold fluids and for fluids to circulate. And we divide our zone of interest up into a rectilinear grid and interpolate our properties in the 3D subsurface. And at each grid point, we'll have a suite of all these different values that we input into the clustering. And this is just a combination of unsupervised k-means clustering, which aims to sort of identify the natural patterns within your data set. And then combining those clustering results together using a consensus function to combine all that evidence and give you a higher level of certainty about your analysis. So it gives you both the uncertainty analysis, but also a very good, it also enables you to pull together a lot of different data sets like we are trying to do. So these are the different properties we're using. Temperature increase with depth. I think that got flipped. Horizontal stress and pressure. This was the first well that was drilled that was treated. And they treated this between April and May of 2019. And all these little stars are the little events that were recorded during that stimulation. So these events tell you basically what's the extent of your fracturing, how well you stimulated the area, what amount of area do you now have that you can circulate fluids from, which is important for engineers in doing calculations of how much geothermal energy they can actually produce in an area and how effective are their models at being able to predict how much they can stimulate. And also in terms of the preventing seismicity, what's our maximum magnitude of seismic event? Are we going to reach that if we start pumping a massive amount of water down there, or do we have to adjust our pumping parameters? We also use porosity, permeability, and vertical permeability. So it's how much it flows in the horizontal XY direction, vertically, and then what's our storage capacity. And this is all data points that are interpolated on a 75-meter spacing. And when we run the clustering, we ran the clustering using all of those 6 different inputs: temperature, pressure, stress, permeability, and porosity. And you apply a partition validity measure to determine the final clustering. And it basically just tells you how measures how alike members of a certain cluster are, and it gives you a certainty. The combination of those can give you better results. So you can see here the different validity measures when combining all that data can give us in our poorest case, it just came up with 2 clusters, basically the basement and all the sediment that's filling on top. But if you want more detail, we can pick these 2 other different validity measures, and they came up with 6 final clusters, dividing sort of the area into different layers, but also along the geology, so along the detachment between the granite and the sediments that are sitting on top of it. And the thing about these clusters is with the hybrid method, we're able to combine these different data sets, which have different units and different measurements. And they measure different things. So we're able to put those together using the hybrid clustering. And this only took me probably an hour and a half to run. So you could almost do it in real time. And the clusters that pulling out are geologically reasonable. It's following this cluster 3 is following sort of the boundary between the basement and the surface sediments. And you can see here that a lot of the microseismic events tend to be clustering in this cluster 3. So we can take a look at the values in that cluster and say, well, maybe, what is it about these properties that make it more likely to have microseismic events at these particular layers. So in summary, basically, we've been able to develop this probabilistic system that's able to pull out these different clusters that broadly mimic the geology of the region. So we can use that to then assess sort of what regions are potentially where we'll potentially have seismicity or not, especially when we combine that with the existing microseismic events, because they are drilling other wells. So we can use that to maybe calibrate models for those other wells. And then the following steps, we want to work on really being able to quantitatively take all those different classes and give them an expert sort of seismic hazard rating, so that we can really fully take the system and make it useful. And that's sort of the end. Do you have any questions?
Okay, well, thank you, and sorry for the delay, etc., and the technical problems. I don't know, and anyone has some questions? So, but Sylvia, I don't know whether you have a question or you just want to thank Sarah. Okay, Sylvia didn't understand the comparison between the methods.
So between the k-means and the transferable belief? Or between...
suppose...
I just want to make sure I understand the question.
Yeah. Well, Celia de Simone, she's in the chat. And she says that you said that one method is better than others.
Oh, okay.
You establish that.
So basically, we're comparing it here to sort of the geology. And with the Fukuyama-Sugeno measure, we're only getting 2. So it's very coarsely. You can compare this to the geology here. It's basically coarsely getting the sediments and the granite. When we're actually trying were to look at the finer scale variations, uh, we want to have this more detail uh, in terms of having more clusters here. So that's sort of why I say these two with more clusters and a little bit more detail than just very broadly it's the sediments and the basement are better.
Yeah. Okay. And then another following up question by Silvia De Simone. So she thanks you and she asks what is the difference between the methods, just briefly.
Well, these are just the validity measures. So basically, the full clustering method has the fuzzy k-means, and the validity measures basically are sort of a goodness of fit test, different sort of goodness of fit tests for your clustering results. So the k-means will basically go in, give you some random centers. It'll measure the distances between the centers and your data points, and divide up your data into clusters based on sort of measures of distance, but also separation, length. And those are what those validity measures are. Uh, we can then take those different validity measures and using the sort of TVM, which is basically just trying to come up with consensus between different data types and also different clustering results, and say, well, you know, these different, we have slightly different results, but our clusters are broadly the same for, these different data types and these different clustering results. So that builds a consensus as to, well, these clusters are more valid than, say, ones that were generated, using the core uh, validity measure. So we can go in and evaluate based on that.
Okay.
I hope that.
Thank you. I, 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 I have just one question a little bit on the data, because you
Mm-hmm.
only use porosity and conductivity data, it seems to me,
No.
or
I have
no, yeah,
temperature
okay,
because we need to have heat. The maximum horizontal stress, because that controls uh, sort of how the rock
okay,
fractures, what direction. Pressure depends on, that also
yeah,
plays a role in the fracturing. And then the porosity and permeability.
yeah,
So there's more data there. And
yeah,
actually, if you go to sort of the Forge DOE website, there's an absolute ton of data. So
yeah,
I
okay,
haven't even tried on putting in like
all the data.
taking geologic
Maybe
maps.
one question. These are all, let's say, it is also about earthquakes, etc. So if you have uh, changes of these things, well, I don't know whether porosity or permeability is very essential, but maybe the stresses may change a lot during these, well, earthquakes events. Do you want to take that into account, or do you take that into account, or is this just the same sort of averaged over time always?
Um, uh, are you talking about looking at the properties sort of in 4D, how they change over time?
Yeah, the
That
change
would,
in time, these of these.
yeah. Well, that's definitely, that's sort of where we want to head.
Yeah,
You know, we sort of have to have a baseline in terms of what is the 3D structure. And then our ideal is to be able to include like pumping data, and because a lot of times during treatments, uh, they'll monitor pressure, formation pressure, they'll monitor the fluid pressures, they'll monitor the changes in porosity and permeability. And the microseismic also gives you an idea of like where you're getting increased porosity and permeability. So being able to take that real-time data is important as sort of the next step
Yeah.
in terms of updating your model in real time.
Yeah. Okay, thank you. I don't know. Any other question? Well, if not, then I thank Sarah Henson for her presentation and the other people for their attendance. And well, maybe we see each other during another seminar. Okay?
Thank you.
Okay, thank you. Bye bye.